Hello, everybody. Welcome back to Math 251. This is lecture 3.1. We have finally graduated from chapter 2. So we're done with all of the harder limit stuff. We will still be seeing limits in this chapter 3, but you have mostly graduated from those tricky limits. So hope you are glad about that. I know that a lot of you probably are. Today's mathematician of the day is Jing Feng, who was a first century BC Chinese mathematician who used math in musical measurements as well as astronomy. You can use math for all sorts of things. And did you know that the only fractions that the ancient Egyptians recognized were those with a 1 in the numerator? So they wrote all other fractions as the sum of their other fractions. So they didn't have 2/3. They had to write 2/3 as 1/2 plus 1/6. So they were really good at their fractions like this. I personally am glad that we have fractions like 2/3. All right, so today is the big day, guys. Today we are introducing the concept of a derivative. This class is called differential calculus. And yes, that word differential comes from this word derivative. So today is a pretty exciting day in Math 251. So you want to buckle in your seatbelts because we are in for a wild ride. All right, we have touched on this first definition the very first day of class, actually. If you think way back to section 2.1, we talked about average rate of change, and we talked about it in terms of secant lines. So if you remember, the average rate of change in f of x on the interval from a to x is the slope of the corresponding secant line, and I'm going to call this m for mx plus b sub secant, and this is equal to change in y, which is f of x minus f of a, over change in x. So this is my slope of the secant line between x and a. We learned about this in the very first lesson. And if I wanted to find the instantaneous rate of change, remember this is the same thing as the tangent line. And we find tangent lines by making this interval from a to x really, really, really small. So the slope of the tangent line is equal to the limit, see there's that pesky limit again, the limit as x goes to a. That's making this interval really, really small. So the limit as x goes to a of f of x minus f of a over x minus a. We are going to be seeing this guy over and over again throughout this chapter. So this is also the slope of the tangent line at the point a comma f of a, provided that this limit exists. The tangent line is the unique line through the point f comma f of a with slope m sub tan, or m sub tan. Its equation is y minus f of a equals m sub tan x minus a. This is in point slope form. So the tangent line going through the point a comma f of a is this thing right here. So this is the difference in y's, this is the slope, and this is the difference in x's. Again, this is point slope form. If you want to rewrite it in slope intercept form, that would be okay too. So we only have one tangent line that goes through every single point. Each point on a curve only has exactly one tangent line, because it only has one possible slope and one possible y-intercept, or point if you want. So let's practice this a little bit. We want to find the equation of the tangent line to the graph of f of x equals 3 over x at the point 2 comma 3 over 2. So I'm going to use the definition of the slope of the tangent line. So we use the definition that we just learned of the slope of a tangent line. I'll just call it m tan, with a equals 2, because our x value here is 2. So I'm going to use this right here. So I know that m sub tan is equal to the limit as x approaches, in our case it's 2, of f of x minus f of 2 over x minus 2. So we plugged in x equals 2 here, since that is where we are trying to find the tangent line. And I know that f of 2, if I were to plug in the value x equals 2 into this guy right here, I get 3/2. So this is equal to the limit as x approaches 2. F of x here is 3 over x. So I have 3 over x minus 3 over 2 over x minus 2. This should look a little bit familiar. We have done a few examples like this in our recitation activity and our written homeworks. So from here, we need to figure out a way to combine the two fractions in the top. And the way that I'm going to do that is I need to find a common denominator in the top. My common denominator will be x times 2. So I'm going to multiply this 3 over 2 by x over x. And I'm going to multiply this 3 over x by 2 over 2 in order to get my common denominator of 2x. So this becomes the limit as x goes to 2 of, now I get 6 over 2x minus 3x over 2x over x minus 2. So I'm going to pause real quick. Why are we doing all of this algebra anyway? Why can't we just plug in x equals 2? Well, just a reminder, if we plug in x equals 2 right now, then we would get 0 in the denominator of this fraction, and we cannot divide a fraction by 0. So that's why we have to do all of this algebra. So now that I have common denominators in my top here, I can combine these two terms. So this becomes the limit as x goes to 2. Combining these two terms gives me 6 minus 3x divided by 2x over x minus 2. Well, what do I do next? Well, I see that I have a fraction and a fraction. So in order to simplify a fraction and a fraction, I keep the top the same, and I multiply this by the reciprocal of the denominator. So basically, I'm going to multiply 6 minus 3x over 2x by 1 over x minus 2. That is the reciprocal of the denominator. So I get the limit as x goes to 2 of 6 minus 3x over 2x times x minus 2. Now I still can't plug in x equals 2. It still makes my denominator equal to 0. But is there something that I can factor out of the top? Well, I can factor out a 3 from each term on the top. Let's see what happens when I do that. So I have the limit as x goes to 2. If I factor out a 3 from each term on the top, I get 3 times, actually, you know what, let's factor out a negative 3. When I factor out a negative 3, I get negative 2 plus x over 2x times x minus 2. Well, hey, check it out. I can cancel this x minus 2 with this x minus 2. And that makes my life so much easier, because now I have the limit as x goes to 2 of negative 3 over 2x, and now I can plug in x equals 2. It no longer makes my denominator equal to 0. So I plug in x equals 2 here, and this is equal to negative 3 over 4. Whew, that was a lot. If you were stuck on this algebra, I do recommend rewinding this and rewatching it to make sure that you understand what all I just did. And remember, this is what did we just find? We just found m sub tam. All right, so I know that, well, personally, I prefer y equals mx plus b form. You could just use point slope form for this, but I'm going to convert this into y equals mx plus b. So I know that y equals mx plus b. I need to find my b value. I have the point here. I have the point 2 comma 3 halves. So I get 3 halves equals our m, which we just found to be negative 3/4, times x, which is 2, plus b. So this gives me 3 halves is equal to negative 3 halves plus b. So b is equal to 3. So my tangent line is y equals negative 3/4 x plus 3. So now if we were to graph these two lines, or these two curves actually, let me pull up Desmos real quick. So I have, whoops. So what does a tangent line look like? Well, I have the line y is equal to 3 over x, which looks like this. And I was at the point 2 comma 3 halves, which is right there. So then if I were to graph my tangent line, we got y is equal to negative 3/4 x minus 3, plus 3. This is what our tangent line looks like. At the point 2 comma 1.5, our tangent line, which is the blue one, just touches our red line at exactly that point. And it also has the same exact slope at the point 2 comma 1.5. So this is what our tangent line looks like. It just touches our graph at one single point, and then it bounces back off. So this is what our tangent line looks like. Again, it has the same exact slope of the red line at the point 2 comma 1/2. So this is what it looks like to have a tangent line. Pretty cool, huh? All right, next we are going to look at another definition. This is similar to the one that we already learned today. The average rate of change in f of x on the interval from a to a plus h is the slope corresponding to the tangent line. So this is just another flavor of the formula for the tangent line that I've already learned, or the secant line that I've already learned, excuse me. So this is the secant line, m sub sec, is equal to, it's still the change in y over the change in x. So my change in y is f of a plus h minus f of a. And my change in x, if I go from a to a plus h, is just h. So this is just change in y over change in x still. And, of course, the instantaneous rate of change at this point, x equals a, is the limit of what we just found above as h goes to 0. So I'm shrinking my interval between a and a plus h by letting h go to 0. That way I make my interval super, super small, and my secant line approaches my tangent line. So I get m sub tan is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. So this is just another flavor of the msec and mtan equation that we just learned, except we name our intervals differently. Here I'm on the interval from a to a plus h, and the other one I was on the interval from a to x. They are equivalent. We can use either one of them any of the time. Sometimes it will be easier to use one or the other, but they are both equivalent, mathematically speaking. And remember, this is the slope of the tangent line at the point a comma f of a, given that this limit exists. All right, we want to find an equation of the line tangent to the graph of f of x equals x cubed plus 2x at the point 1 comma 3. And I want to use the definition that I just learned. So just to remind ourselves, the slope of the tangent line, using the definition that we just learned, is equal to the limit as h goes to 0 of f of a plus h minus f of a over h. So I need to find, oh, and what is our a here? Well, our x value here is 1. So this means that a is equal to 1. So we can go ahead and plug that in here. This is the limit as h goes to 0 of f of 1 plus h minus, well, f of 1 is just 3. So this is 3 over h. But I need to find f of 1 plus h. In order to find f of 1 plus h, I have to plug in 1 plus h wherever I see an x in my function here. So f of 1 plus h is equal to 1 plus h cubed plus 2 times 1 plus h. Well, let's break this down a little. Oops. Let's break this down a little bit. Oh my gosh, what just happened? So sorry. Ooh, sorry about that. I pulled up a tab. So 1 plus h cubed. Let's do 1 plus h squared first. So I have 1 plus h squared times 1 plus h plus 2 times 1 plus h. Okay, so 1 plus h squared is 1 plus 2h plus h squared. That is 1 plus h squared. If you don't believe me, fill it out. And then I'm going to multiply this by 1 plus h again, plus 2 times 1 plus h. Well, this is equal to 1 plus h plus 2h plus 2h squared plus h squared plus h cubed plus 2 plus 2h. And combining like terms gives me, let's see, I have h cubed plus 3h squared plus 5h plus 1. So this is f of 1 plus h. Oh, actually, sorry, it's plus 3. Plus 3. I have a 1 and a 2 here. So now I can plug this whole expression in for this guy. We just found f of 1 plus h. So this is equal to the limit as h goes to 0. F of 1 plus h is h cubed plus 3h squared plus 5h plus 3. And then I have this minus 3. All of this over h. Well, my 3's cancel. And I am left with the limit as h goes to 0 of h cubed plus 3h squared plus 5h over h. Well, I can't plug in 0 yet because I still have this h on the denominator, but I can factor out an h from each of the terms on the top. And that's what I'm going to do. So when I factor out an h from every term on the top, I get the limit as h goes to 0. And then I have h times h squared plus 3h plus 5. Ooh, plus 5. Over h. Now these h's cancel. And so I have the limit as h goes to 0. All I'm left with is h squared plus 3h plus 5. And now I can just plug in h equals 0. When I plug in h equals 0, I get 5. So 5 is m sub tan. This means that the slope of our tangent line of the graph x cubed plus 2x at the point x equals 1 is 5. Now I just need to plug in my point to solve for b in our y equals mx plus b form. So I have y equals mx plus b. My y is 3. My slope I just found to be 5. My x is 1. So this gives me 3 equals 5 plus b. So b equals negative 2. So my tangent line is the equation y equals 5x minus 2. if I want to see what this looks like on Desmos, and I do, let's pull up this graph. X cubed plus 2x, y equals x cubed plus 2x. So that is the red line. I am at the point 1, 3 right here. And I want to graph y equals 5x minus 2. So this blue line just touches the graph at the point 1, 3. It bounces off and then it continues on. So this graphing is a good way to check it. In this case, we definitely did this right because our tangent line looks a-okay. So we are good to go. I know that this is a lot of algebra, especially finding this like f of 1 plus h business. So it might be a good idea to brush up on some foiling or expanding if you're not super comfortable with it. All right, here it is, guys. Here is the definition of the derivative. I hope you are as excited as I am. I know that I am just on the edge of my seat. I just can't even wait. Okay, you ready? The derivative of f at the point A, we call it f prime of A, is given by either of the following two limits provided that they exist and that A is in the domain of f. So these should look familiar because we've already seen them in this lesson. The first one is f prime of A equals the limit as x goes to A of f of x minus f of A over x minus A. This was the first definition of the tangent line that we learned today. Or the second version of that tangent line was f prime of A equals the limit as h goes to 0 of f of A plus h minus f of A over h. Now these two formulas are representing the same exact thing mathematically. The only difference is that in the blue one, we are on the interval from x to a, and on the red one, we are on the interval from a to a plus h. That's the only thing that is different about these. They can be used interchangeably. They are the exact same thing mathematically. So we have seen these in terms of the slope of a tangent line. So it's important to note that these two expressions represent the slope of a function f at a point A. So the derivative at a point equals its slope. Right, because we saw that if I find the slope of a tangent line of a function, it's the same as the slope of that function at that point. So the derivative of a function at a certain point is the same value as the slope of that function at that point. So this is really important here. Derivative equals slope. Very important. So for example, if I had a straight line as a function and I was asked to find the derivative, I could just compute the change in y over change in x. That's my slope of my line, right? That's the derivative. It's just the slope. All right, we have a couple more examples. In example 3, we have f of x equals square root of 3x minus 1. And we want to compute f prime of 3, or the derivative of f at x equals 3, and use the result to find the equation of the line tangent to the graph at the point 3, 2. So this f prime of 3 business right here, remember, this is the slope of f at x equals 3. That's all this is. So I can use either this guy or this guy over here. I can use them interchangeably. I'm going to use the first one for this example. So using this equation, I get that f prime of 3, so here my a value is equal to 3, so this is the limit. So this means a equals 3. So the limit as x goes to 3 of f of x minus f of 3 over x minus 3. All right, well, this is the limit as x approaches 3. F of x is simply the square root of 3x minus 1. And I know, because it gives it to me, I know that f of 3 is equal to 2 over x minus 3. So this is, if I combine my -1 and my -2, this is the limit as x goes to 3 of the square root of 3x minus 3 over x minus 3. So I can't plug in x equals 3 yet, right? Because it makes my denominator equal to 0. But if I see an expression like this, square root of 3x minus 3, I'm hoping that for some of you, it kind of gives you a tip as what to do next. When I have something like square root of 3x minus 3, what I'm going to do here is I'm going to multiply it by there's a special word for this, by the conjugate. So I'm going to multiply the top and the bottom of this fraction by the conjugate of the square root of 3x minus 3. And the conjugate here is the square root of 3x plus 3. So I'm going to multiply the top and the bottom of this fraction by square root of 3x plus 3. If you have an expression like this, it's generally a good idea to multiply by the conjugate because some stuff cancels out and everything will be okay again. So when I do this here, I get the limit as x goes to 3. And when I multiply by a conjugate like this, what I get is I get the square root of 3x quantity squared. So that multiplies out to just 3x. And then I have minus 3 plus 3 because my middle two terms cancel when I FOIL this out. So I get 3x minus 9 when I FOIL this term with this term over x minus 3 times square root of 3x plus 3. Well, I still can't plug in x equals 3, but if I notice on the top here, if I factor out a 3, I end up with the limit as x goes to 3. Factor out a 3 from the top and I end up with an x minus 3. Square root 3x plus 3. Which is great because now this x minus 3 cancels with this x minus 3. And I'm left with the limit as x goes to 3 of 3 over square root 3x plus 3. And now I can plug in x equals 3 because it's no longer 0 in the denominator. When I plug in x equals 3, I get 3 over square root of 9 plus 3, which is 3 over 3 plus 3, or 3 over 6, which is 1/2. So this is, remember, the slope of the tangent line, m sub tan. And now we want to find the intercept of this. So I want, the slope-intercept form. So I want to plug into y equals mx plus b. I have my y point, it is 2. My slope I just found to be 1/2. My x value is 3 plus b. So I get 2 equals 3/2 plus b. So b equals 1/2. And my tangent line is equal to y equals 1/2 x plus 1/2. How much fun was that, you guys? I don't know about you. I had so much fun. That was some great math. So hopefully this made sense to you. Again, I know that it is a lot of algebra. So again, feel free to rewind this if you are having trouble with the algebra. Hopefully this video, the fact that you can rewind and stuff helps you with stuff like that. All right, we have one last problem. This is a word problem. So we have sound intensity I measured in watts per square meter at a point x meters from a sound source with acoustic power P is given by this equation here. A typical sound system at a rock concert produces an acoustic power of about P equals 2W, 2 watts, compute I prime of 2 and interpret the result. So there's a lot of variables here, but we want to find I prime of 2 when this p here equals 2. So I'm going to find the derivative at the point 2 of I. And I am going to use, I'm going to use the second definition of our limit here. So this h goes to 0, 1. So I want to find I prime of 2. And according to our definition of how to find derivatives, this is equal to, using the second definition, the limit as h goes to 0 of I of 2 plus h minus I of 2 over h. So wherever I see an x in my original function, I need to plug in 2 plus h. So this gives me the limit as h goes to 0. My p, my power here, is 2, since I know that my the acoustic power at a rock concert is about 2 watts. So I have 2 over 4 pi times 2 plus h squared. This is I of 2 plus h, minus I of 2, that's just 2 over 4 pi times 2 squared, all of this over h. Okay, well this simplifies a little bit. I'm going to cancel this 2 with one of these. And I'm also going to cancel this 2 with this 4 here, and I'll be left with 2 here. So let's go off to the side here. So right now I have 1 over 2 pi times 2 plus h squared. And this equals 1 over 2 pi. If I FOIL this out, I get 4 plus 4h plus h squared. So I am left with 1, if I FOIL this out again, I get 1 over 8 pi plus 8 pi h plus 2 pi h squared. But actually, now that I'm looking at it, this is, correct and everything. But because I want to subtract these two, I need to find a common denominator first. So, yeah, that's still right. But anyway, so we need to find our common denominator. So if I rewrite this, I have the limit as h goes to 0. I have 1 over 2 pi times 2 plus h squared minus 1 over 8 pi. So I see that my common denominator should be 8 pi times 2 plus h squared. So I need to multiply, oh, and all of this is over h, of course. So I need to multiply this guy by 2 plus h squared on the top and the bottom. And over here, I need to multiply this side by 4 over 4 to get my 8 pi in there. All right, so I have the limit as h goes to 0. This becomes 4 over 8 pi times 2 plus h squared minus 2 plus h squared over 8 pi 2 plus h squared. All of this over h. Now I can combine these two factors in the top now that I have a common denominator. So that's what I'm going to do. This will become the limit as h goes to 0. Combining these two in the top gives me 4 minus 2 plus h squared over 8 pi 2 plus h squared. All of this over h. All right, so Now that I have my fraction and a fraction, I'm going to keep the top as is and multiply it by the reciprocal of the denominator. So I'm going to multiply this by the reciprocal of h, which is just 1 over h. So I get the limit as h goes to 0 of 4 minus 2 plus h squared over h times 8 pi 2 plus h squared. Now I still can't plug in h equals 0 because of this term right here. But let's see what happens if I simplify my numerator here. So I get limit as h goes to 0. I have 4 minus, if I expand out this term, I get 4 plus 4h plus h squared over h times 8 pi 2 plus h squared. And this 4 cancels with this 4. If I distribute this negative to both of these, I get the limit as h goes to 0 of minus 4h minus h squared over h 8 pi 2 plus h squared. And everything is good and right in the world again because I can factor out an h from the top. Whew. When I do that, I have the limit as h goes to 0. Factoring out an h from the top gives me h times negative 4 minus h over h 8 pi 2 plus h squared. So these h's cancel. Now I can plug in h equals 0 since it is no longer 0 in my denominator. When I do that, I get negative 4 on the top, 8 pi times 2 squared, which is negative 1 over 8 pi. Wow. So that is the derivative of my function I of x at the point 2. So what does this mean in the context of this problem? Again, we're talking about sound intensity, and this function I is giving me my sound intensity at a certain point x meters from a sound source with a certain acoustic power. Well, this negative here tells me that the intensity is decreasing. So what this means in the context is the sound intensity decreases with an instantaneous rate of change. Instantaneous rate of change of 1 over 8 pi, I don't include the negative since I say that it's decreasing, watts per meter squared at the point, since I was at x equals 2, so at the point 2 meters away from the sound source. So this is a pretty good example of a kind of word problem that you could expect in this situation. So rates of change they have a lot of applications. Maybe we can talk about that next time. I know this one is already running a little bit long. But yeah, rates of change are everywhere. If you tell me your major, I will tell you how derivatives are related to your major. They are literally everywhere, and they are very important to a lot of jobs out there. So yeah, maybe we'll talk about that more next time. Yeah, I hope you learned a lot today. I know I had a lot of fun. Hope you did too. And that's it for today. So I'll see you next time.